This is Cycle 1, Lesson 1 of the Advanced Functions course, identifying graphs of basic polynomial functions. Cycle 1, Lesson 1, in other words, this is the first lesson of new content that's specific for the grade 12 course. And we're going to be talking about polynomials for the next few lessons anyway, more than a few probably. I haven't actually counted them. Anyway, so we're going to look at graphs of polynomial functions. In fact, this whole first cycle, before I get into the specifics for today, this first cycle, cycle 1, has a lot to do with graphs, looking at graphs of different types of functions. We're going to look at polynomial functions and rational functions and exponential functions and trigonometric functions. We're just going to be looking at the graphs of them a lot in this unit. All right? So let's jump into today's lesson. So first of all, we have a table. Polynomial function in the general form, and we've got a list of different types of ones. So the first one here, we got y equals ax plus b. That's basically, hopefully you recognize that as linear. You swap out the a for an m, and that is y equals mx plus b. It's a linear function. But think of it like a polynomial function. What's the degree? Remember, the degree is the largest exponent within the polynomial. And it has to be in standard form. So in this case, these are all in standard form. The first one is degree 1. The largest exponent is the 1 that's assumed to be on the x, even though it's not actually, I've handwritten it in, and you don't see it there unless you write it in yourself. It's a degree 1, right? And that's linear. All right, the next one is quadratic. It's degree 2. Let me just get rid of, I don't want to have stuff piling up for the highlighting. So the next one is degree 2. I can tell that because of the 2 that's on that. That's my highest exponent. That's what makes it degree 2. That's what makes it quadratic. The next one, degree 3. That's my highest exponent, and that's what we call cubic. And then the next one's degree 4. And we actually have a name for that. That's called quartic. A power function is the simplest type of polynomial function. So polynomial functions, these are all polynomial functions here. And they can have a quartic function, for example, could have up to 5 terms, but it could have as little as 1 term. It could just get by with this term here and still be quartic, right? So if you just have the 1 term and it is whatever degree it is, that's called a power function. So it's in the form ax to the n, where x is the variable, a is a real number called the leading coefficient, and n is a whole number, it's the exponent. Pardon me, jumped around on me again. All right. So let's look at some specific ones. Again, this is pre-filled in to save us some time as far as the video lesson here goes. But you can play around with these on Desmos if you want to. So y equals x. What does that look like? Well, it looks like a straight line going through the origin as I've drawn there. The power function, that is the power function. And it's assumed this power function has an a value of 1. It's got an n, an exponent of 1, but neither of those things are usually written in. You can see, if you read this, well, let me back up for a second. Let's talk about the domain and range. The graph, as you can see, is going to continue to infinity out towards the left. It's going to continue out towards the right, towards infinity. In other words, thinking about the domain, it's going to go this direction forever, it's going to go this direction forever. I can keep going in both directions on this line. The domain is all real numbers. As far as the range goes, it can go down forever, it can go up forever, right? So the range is also all real numbers. Now, end behavior. Let's pay close attention to this. If you're looking at the graph and you're reading it from left to right, so let's say you're starting here on this end, somewhere You know, we don't start, it goes from, it starts at infinity, but let's just start anywhere. And we start reading this graph as we're going towards the right. What's happening? So it says as x arrow infinity. So all that's saying is as x moves towards infinity. So again, just to draw it so you can see it, as we move along the x-axis from somewhere out on the left, as we move towards the right, that's x tending towards infinity. That's x moving towards infinity. All right? So what's happening to the range, or to the graph in general, as we move along the x-axis from left to right? Well, what's happening is that we're starting in quadrant 3 and moving towards quadrant 1. So again, as we move along this graph from left to right, we're starting in quadrant 3 and we're ending up in quadrant 1. That's what that bottom line there is saying. The quadrants, by the way, go 1, 2, 3, 4, like that. Okay? So that's end behavior. We're going to talk a lot about end behavior, so keep that in mind. The next one, quadratic. I know it's quadratic because it's degree 2. That's my n value. It's still got an a value of 1 implied. That's my power function. That's my parent function. All right? For quadratic, we know that y equals x squared is a parabola at the origin, as you can see in the graph there. What's the domain? Well, the domain's all real numbers. Everything's possible. The range is all real numbers that are greater than or equal to 0, because that's where the vertex is. As I go from left to right, so start at the farthest left part of the graph, so let's start about here, and if I just follow the graph as it moves from left to right, what's happening? Well, what's happening is I'm going from quadrant 2 to quadrant 1. So that's what the end behavior is for this quadratic. The next one, degree 3, is called cubic. And we can graph this. Again, in the interest of time, I'm not going to do it in this video, but if you type y equals x to the exponent 3 into Desmos. Sorry, it keeps jumping on me every time I undo something. If you type y equals x to the 3, if you type this into Desmos, you'll get a graph like I've drawn here. I won't fill it in this time, but imagine starting at the left-hand side of that graph and following it along to the right. What's happening? Well, it's starting in quadrant 3 and ending in quadrant 1. That's what we have at the bottom. As far as the domain and range goes, I skipped over that. Well, again, we can see there's no breaks in the graph. It's going to cover all the x values. It's very similar to the linear one, except that it's got a curve in it, right? If you look at this graph here compared to this graph here, they're doing very similar things, except that the cubic one has got a curve built into it. And so it's got the same domain as the linear one, it's got the same range as the linear one, and it has the same end behavior, quadrant 3 to quadrant 1. Jumping to the next one, now we've got the linear again, y equals negative x. What's different though? Well, clearly what's changed compared to the one above it is that the negative sign is in front of the x. So we've got a negative leading coefficient. And we know from grade 9 that if we've got a negative leading coefficient, that's really just a negative slope in terms of linear. And so it's going to be a line going down from left to right. The domain's still the same, still goes all real numbers from left to right. The range still is anything from up or down. We can go up or down as high as or low as we want with no breaks, all real numbers. But now, as far as the end behavior goes, we're again starting on the left and going to the right. We're going from quadrant 2 to quadrant 4, right? So there you have it. Quadratic is the next one. Again, we've already seen a quadratic, but what's different about this one is the negative sign. All that's done is flip the parabola upside down, flip it in the x-axis. So What's the same? What's different? Well, the same thing is the domain. That hasn't changed. The range is different because now having the origin, the vertex origin as the lowest point, that's what it was before, now that's the highest point. So instead of being all values that are greater than or equal to 0, as in this one, it's going to be all values that are less than or equal to 0 in this one. That changes the end behavior as well. So what that means now is that we're going from quadrant 3 to quadrant 4. Again, here we have a cubic one. Hopefully you're getting the idea now. So you can see the domain's all real numbers, the range is all real numbers because it's been reflected in the x-axis, again, due to that negative sign. That just flips things in the x-axis. And that means that we're now going from quadrant 2 to quadrant 4. Again, notice how that end behavior is the same as the end behavior for the linear function with the negative leading coefficient. Whoops, done. Oh dear. Here we go. All right. What have I done? Things are stuck on me. That's the problem with... There we go. Okay. Sorry. Little bit of a technical glitch. We're back on track. Anyway, so 2 to 4 in both cases. Going higher up, now we have higher up the exponents. We have an exponent 4. We saw that's called quartic. That's what the graph looks like. It sort of looks like a U, a boxy parabola. Again, you can do that in Desmos yourself. You could type y equals x to the 4 in there. It's going to look sort of like a boxy parabola, which means it's going to behave very much like a boxy parabola. It's going to have the same domain as a parabola. It's going to have the same range as a parabola. It's also going to have the same end behavior as a parabola from quadrant 2 to 1. Go back and compare that to our quadratic, but not the one that was reflected in the x-axis. Quintic, degree 5. All right, that's what's changed for this one. It looks very much like the cubic and linear. It's got the same domain, same range, same end behavior, 3 to 1. Sextic is degree 6. Again, it looks like a parabola. Again, even boxier still, but still with the same features as a parabola. Same domain, same range, same end behavior. Here we have the exact same things except reflected in the x-axis. So all those three I just looked at, all we've done is add a negative sign in front of each one of them. So the domain and range, the domain will stay the same for each of them. The range for the quartic now becomes less than or equal to 0. And the end behavior now goes from 3 to 4, just like the end behavior for a reflected quadratic. For quintic, it's again just like a reflected cubic or reflected linear, same domain, same range, end behavior switches to 2 to 4. For sextic, that's going to be working the exact same way as quartic or quadratic. So if that went by quick, you can pause it, think about it, rewind it if necessary, but it all is, what we're seeing is it's all following a pattern. And the pattern is that if they're odd, if it's an odd degree function, which ones were odd? Well, the odd ones were linear, cubic, and quintic, right? If it's an odd degree function, they all behave as if they were linear. In other words, linear is a very basic kind of parabola, and cubic follows the same behavior, same end behavior, same domain, same range as linear does, and so does quintic follow that. So I can describe them as behaving like a linear function. And all those linear functions, again, we can go through them, end behavior, 3 to 1, quadrant 3 to quadrant 1, quadrant 3 to quadrant 1. Let's go down to quintic, quadrant 3 to quadrant 1. So if I want to find a possible equation for a power function whose graph extends from quadrant 3 to quadrant 1. I need to have an odd one, but it has to have a positive leading coefficient. If I want it to be a power function, it shouldn't have these extra bitties on the end, so I'll get rid of them. So there's a couple power functions that have positive leading coefficients. They're odd, and they go from quadrant 3 to 1. If I want to find a power function that goes from quadrant 2 to quadrant 1, well, there was a certain group that did that. And that group was the even degree functions, like quadratic, like quartic, and like sextic. They all went from quadrant 2 to quadrant 1 as long as they were upward facing. And they're upward facing if they have a positive leading coefficient, like y equals 3x to the 6, or y equals 7x squared. Something like that. If I want to go from quadrant 2 to quadrant 4, then we're back to odd again, right? So these are like linear, the linear that's been reflected. Where's a reflected linear one? There it is. Reflected linear one goes from 2 to 4. Reflected cubic goes from 2 to 4. Reflected quintic goes from 2 to 4. So they're all odd. They all have a negative leading coefficient. And then we have what's left, quadrant 3 to 4. As long as they look like an upside down parabola, in other words, as long as they got an even exponent and have a negative leading coefficient, they're going to go from quadrant 3 to 4. Okay, symmetry in power functions. A graph has a line of symmetry if there is a line y, x equals a, that divides the graph into two parts such that each part is a reflection of the other in the line y equals a. Think back to parabolas. Remember your axis of symmetry? That's really the kind of thing they're talking about. So if we have a axis of symmetry or a line of symmetry, then that's what we're looking for. Well, what kinds of graphs had that line of symmetry? Well, the power functions that have even exponents. So they have to have the exponent 2, 4, or 6. It doesn't matter. They can have different leading coefficients. You know, they could have a 3 here, or a negative, or a -7. It doesn't matter. They're still going to have line symmetry. In general, all even degree functions have line symmetry. Again, if they're like a parabola, if it looks like a parabola, it has line symmetry. Point symmetry might be new to you, and that is if we can rotate it around a central point 180 degrees and have it look exactly the same as we started, that's considered point symmetry. And so here's a picture. Imagine if I stuck a thumbtack in that red dot, the dot right here, stuck a tack in that, and then spun the whole shape around 180 degrees, it would look exactly the same. Another way I can think of it is if I reflect it twice, if I reflect it this way and then this way, reflect it horizontally and vertically, and it still gets back to what I started with, that also would satisfy that point symmetry idea. Which ones look like this? All the odd functions. So y equals x to the 3, y equals x to the 5. Again, they can have anything in front of them. They can have any number in front of them, that is, any leading coefficient, positive or negative. All right, that doesn't matter. But that's point symmetry.